The Riverside Park network operates as a highly connected terrestrial corridor, maintaining a continuous canopy that serves as the Sid Valley's primary wildlife highway. This contiguous green infrastructure allows keystone species to manipulate the environment. Eurasian beavers navigate this unbroken terrain, acting as active habitat creators by modifying water flow and felling timber. European otters follow these same terrestrial and semi-aquatic routes. They operate as the ecosystem's apex predators, effectively serving as biological shields that keep smaller mesopredator populations in check. Above the ground layer, the uninterrupted woodland creates a protected aerial superhighway, supporting the feeding and navigation routes of at least 11 distinct bat species. This 3D topographical map of the Sid Valley quantifies the density of this isolated zone. Despite its narrow footprint, the network holds 73.3% of the broader area's tree and shrub species, alongside 60% of its ferns. The density of the terrestrial flora and the mobility of the mammalian fauna suggest a perfectly intact ecosystem. But looking below the canopy reveals a severe structural contradiction. The aquatic system, the river running directly through the center of the habitat, is completely shattered. Across the valley floor, human engineering has severed the watercourse with 27 distinct man-made weirs and culverts. Structural connectivity is not universal. The Sid Valley possesses a thriving, contiguous roof, but its aquatic floor is fragmented, preventing the terrestrial and riverine systems from functioning as a single, unified biological unit. Conducting a spatial SWOT analysis, mapping strengths, weaknesses, opportunities, and threats across physical dimensions, requires separating the engineered strengths of the land from its historical scars. The immediate strength of the network is its diverse habitat mosaic. The geography alternates between broadleafed woodland, neutral damp grassland, and vital hedgerow scrub. This diversity is artificially maintained. Conservation groups deploy multi-purpose management philosophies, relying heavily on precise cut and remove, grazing and mowing regimes to stop fast-growing flora from establishing a monoculture. In specific nodes, like Livonia Road Field, the management strategy is intentional neglect. By allowing the scrub to grow unruly, they create a soft edge that serves as a protective sanctuary for small mammals and nesting birds. However, mapping the weaknesses reveals deep biological scars. The soil matrix throughout the park network is heavily influenced by its past life as cultivated farmland. This comparative layout isolates the grassland layer to show the lingering effects of historical livestock grazing. While certain mammal populations thrive, grass diversity is suppressed, recording only 23 out of an expected 45 survey species. The legacy of human cultivation means the soil actively supports high populations of aggressive brownfield and disturbed land species, which continually compete with native botanical variants. Modern behavioral patterns add a second layer of pressure. The network borders dense residential housing and sustains heavy daily recreational use. The constant presence of off-leash dogs creates a persistent acoustic and olfactory threat. This proximity forces local mammals into hiding and suppresses the establishment of waterside bird populations. The terrestrial network is a recovering, traumatized agricultural landscape. Left alone, it would devolve. It requires aggressive, continuous human curation to maintain its baseline biodiversity. Dropping from the terrestrial canopy down to the surface mechanics of the main river exposes a more urgent set of spatial failures. This cross-section highlights the network's primary bottleneck, the school weir, a sheer 2.5-meter concrete wall dissecting the river. Ecologists classify the structure as a superfragmenter. It creates an impassable vertical cliff, halting the upstream migration and spawning cycles of local fish populations. The natural flow of the Sid compounds the issue. The river has an inherently high water velocity, which creates turbulent conditions that prevent aquatic insects, like odonata dragons and damselflies, from successfully breeding. The physical architecture is overrun by a secondary threat, invasive fauna. The American signal crayfish inflicts multi-pronged damage. They consume fish eggs off the riverbed, carry deadly plague, and carve deep horizontal burrows that weaken the soil bank's structural integrity. Above the waterline, the American mink operates as a highly efficient predator, decimating the already fragile, recovering populations of native river mammals. The most pervasive threat is floral. Himalayan balsam occupies over half the river's length. The danger is mechanical. Its roots are exceptionally shallow. When the plant dies back in winter, it leaves the riverbanks unsupported, resulting in massive soil erosion. These anthropogenic barriers and invasive species actively dismantle the physical architecture of the river course, transforming a productive habitat into a degraded, high-friction environment. The spatial audit expands outward. The health of the immediate river corridor is entirely dependent on the macromechanics of the upper catchment zone miles upstream. The Sid is a flashy river. It reacts to heavy rainfall with extreme volatility, channeling massive water volumes into sudden, violent flash floods. The mechanical consequence of a flashy river is extreme friction. The sudden rush of deep water physically scours the riverbed, washing away the fragile, carefully constructed gravel nests required for fish spawning. This isometric map tracks the secondary threat triggered by these storms. Rain hits the adjacent agricultural fields in the upper catchment, generating dense chemical runoff that drains directly into the clean water channels. This runoff is saturated with nitrates and phosphates from industrial farming. As floodwaters pass, they drop thick, chemically dense sediment. This physically smothers surviving gravel beds, choking out the remaining aquatic life below. Localized downstream conservation efforts cannot gain traction if upstream flash floods and chemical discharge continually strip the riverbed of its biological gains. Counteracting this systemic instability requires the opportunity phase of the audit, active remediation. Conservationists have launched the Opening the Sid project to forcefully re-engineer the habitat. Bypassing the school weir requires intensive structural intervention. Teams are investigating the carving of technical bypass channels and the installation of dedicated eel ladders to restore vertical migration routes. This schematic maps in-stream manipulation. Anchoring logs, or tree kickers, into the bank deflects fast water, carving deep pools for fish. Above water, ecologists use skylighting. Thinning the tree canopy allows direct sunlight to penetrate, triggering the rapid regeneration of essential aquatic plants. To counter the destructive flash floods, teams execute the labor-intensive process of manually seeding the riverbeds with tons of fresh gravel, physically replacing the spawning grounds washed away during storms. Terrestrial biological control requires equally precise tactics, specifically the localized deployment of a semi-parasitic plant called yellow rattle. Volunteers sow yellow rattle directly into the fields. The plant naturally locks onto and suppresses the root systems of dominant, vigorous grasses, opening up the soil space needed for delicate native wildflowers to take hold. These interventions prove a hard ecological rule. Nature cannot organically heal itself within a heavily modified landscape. It requires aggressive, calculated engineering to artificially mimic the natural processes that humans previously erased. The final phase of securing the network scales up to macro-level policy. Fixing the Sid Valley requires implementing catchment-wide natural flood management, or NFM, protocols. This topographical map tracks the effect of NFM interventions. By installing leaky dams and designated attenuation ponds in the high ground, authorities can trap massive storm pulses, physically defanging the flashy hydrology before it ever reaches the vulnerable valley below. Biological policy is also tightening. The network is currently undergoing strict preparations for the reintroduction of the water vole, locally extinct since the 1980s, by legally designating and enforcing strict mink-free zones. Protecting this heavily engineered state from surrounding urban encroachment requires a rigid legal framework to shield the corridor from development and artificial light pollution. Local government has implemented a mandatory 20% biodiversity net gain requirement. Any new human development in the area must legally prove it will increase the aggregate ecological value of the land, forcing construction to subsidize conservation. The survival of the Riverside Park ecosystem relies entirely on an enforced, highly managed equilibrium. Through structural connectivity, upstream flood mechanics, and relentless biological engineering, the valley dictates the terms of its own survival.